Hi there. We're back for more of thermal energy. We've finished talking about some of the basic concepts in thermal energy. What is thermal energy? How is it transmitted through solids, liquids, and gases by conduction, convection, and radiation? We've talked about insulators and conductors, what temperature is in terms of the particles of matter. We've talked about particle theory. So we've covered a lot of the foundational work. Now I want to start looking at how we measure or quantify. So you had a day or two off without your calculators, but you had to know that it wouldn't last that long. So we are back, and I want to spend some time. Today we'll just do a short note. I'm going to do half of section 2.3. All of 2.3 is a big chunk, so I'm going to break it up into two smaller bits. So this will be a short class today. Right, so today we're going to start by looking at heat capacity. Right, heat capacity is a concept that we use to say how much thermal energy is transferred. Remember, heat is defined as the quantity of thermal energy transfer. So in this case, if I'm causing something to heat up or cool down by either adding thermal energy or removing thermal energy, right, I can quantify that amount. I can calculate how much thermal energy transfer there's going to be. And rather than using delta E for the change of energy, we usually typically have tried to make this a little bit easier and just talk about a single quantity, which is called heat transfer. And the symbol is Q for the quantity of thermal energy transfer or quantity of heat transfer. Now, some of these things should make sense. If I wanted to heat up a pot of water and I put it on the stove and I want to bring it to a boil, if I really want it to boil fast, I'm not going to put any more water in than I need to, because the more water that's in there, the longer it's going to take to boil. Right? That makes sense, because the more energy is going to be required, the more heat is going to be required. So it turns out there's a direct relationship between the amount of thermal energy, heat transfer required, and the amount of mass that's required to achieve the same temperature change. More matter means I need to heat it more. Number two, if I want to heat it more, right, I have to add more energy. So it's, again, a direct relationship between the amount of heat required, Q, and the amount of temperature change I'm going to get. If I double Q, double the energy, I will double the temperature change. In order to double the amount of mass that I'm heating up, I need double the amount of thermal energy. So I've got those two direct relationships. Now there's a missing piece here, and it turns out that when I'm heating something up, not all matter absorbs energy at the same rate, right? So different types of matter have different capacities for absorbing heat, different abilities to process that heat that's being transferred to it. So we've got a new variable here. The variable is called the specific heat capacity, and it's given the symbol C. Now, C, the specific heat capacity, says how many joules of energy are required to raise the temperature of 1 kilogram of matter by 1 degree Celsius. So if I'm talking about liquid water, I know that if I want to raise the temperature of 1 kilogram of water by 1 degree Celsius, I need to add 4,200 joules of thermal energy. That's what C is. It's how many joules of energy are required to raise the temperature of 1 kilogram by 1 degree Celsius. Now, if I want to raise the mass temperature of 2 kilograms, I'll need twice as much energy, right? But this is the amount that's going to be used as our baseline for joules required per kilogram per degree Celsius. So if Q is directly proportional to mass, and Q is directly proportional to temperature change, and Q is also proportional or related to the specific heat capacity, then we can bring this all together by using Q in joules, M in kilograms, delta T in degrees Celsius, and C in joules per kilogram degree Celsius. We get a direct linear relationship between these three variables, and we get the formula Q is equal to M times C times delta T. Right? So this is our formula for thermal energy. Right? If I want to raise the temperature of 0.4 kilograms of water, so I need the C value for water, by 10 degrees Celsius, I can calculate how much thermal energy I require. So M is easy, how much matter is there? Delta T is easy, just use a thermometer to find the temperature change required. C, what about C? Well, I need someone to tell me what C is. So typically, we will be given a table on the test that will tell us what are the C values for different types of matter. So it turns out that for water, it's 4,180 joules of energy required to raise the temperature of 1 kilogram by 1 degree Celsius. If I have ethyl alcohol, which is a liquid, and I want to increase it, I only need 2,460 joules to raise the temperature of 1 kilogram of ethyl alcohol by 1 degree Celsius. Now notice that if I've got some metals here like aluminum, aluminum only needs 920 joules to raise that temperature, a lot less than water. If I've got iron, 450, copper, 380, silver, 240 joules, lead, 130 joules. So notice that the solids here, glass, 840 joules. So the solids seem to be a lot less than water, but water is the exception. Again, remember water is that magic molecule. It's got its own properties. It has its own set of rules that it lives by, and we have life on Earth because of the properties of water. Now, you can see that if I've got solid water here, it absorbs energy differently than liquid water. So not only do I need to know what type of matter are we talking about, but I also need to know what is the state of matter, because different matter in different states will have different C values. So this column here is C. This is the specific heat capacity, and it's measured in joules per kilogram degree Celsius. Q equals MC delta T. Right, so I'm going to very quickly just do the 3 sample questions that are here, and then I'm going to leave you to try some of these on your own. Okay, so here are the 3 sample problems. Again, notice that sample problems are pretty long. It says, if 200 milliliters of water is heated from 15 degrees Celsius to 40, how much thermal energy is going to be absorbed by the water? Now, how much thermal energy is going to be absorbed? I'm going to go to my whiteboard here. This is sample 1. Okay, this is sample 1. And I'm going to make my writing just a bit bigger here. Maybe I won't. Oh, there it is. Let's just go to there. Okay, so we know, let me just get my question here. I've got the question written down. It says I have 200 milliliters of water. I know that it's water, and I know T1 is 15 degrees Celsius. And T2, the final temperature, is 40 degrees Celsius. Okay, so the other thing that I'm told is that it's water. And it is, if it's starting at 15 and ending at 40, I know that it's got to be liquid water, because if it was less than 0, it would be solid. If it would be more than 100, it'd be a gas. But at 15 and 40 degrees, it's going to be liquid water. So I know the C value for water is 4.18 times 10 to the third. Oh, come on. Third joules per kilogram dot degrees Celsius. Okay, again, notice that we've got a dot product going on here because I'm basically multiplying things that shouldn't be multiplied together. The dot product allows me to do that. Now, the question is, how much thermal energy is required to warm this water up by 15 degrees Celsius. Now, to do Q, I need to know the mass of water. I need to know the C value for water, and I need to know delta T for water. Now, I know the C, and I know delta T, T2 minus T1. I don't know the mass yet, but what I do know, one of the nice things about water is 1 gram is equal to 1 milliliter. So if I use my conversion here, I know that 1.00 grams of water is the same as 1.00 milliliters of water. Here we are with our unit conversions again. Notice that the milliliters disappear and I'm left with grams. So 200 milliliters will be 200 grams. So now, again, I need to know my units here for C are in joules per kilogram degree C. So again, notice that I've got a problem here that I have grams. So I'm going to say if a kilogram is the same as 1,000 grams, oops, then my grams will cancel and I will end up with 0.2000 kilograms. Okay, so there's my mass. So now I can do my Q is equal to the mass, 0.2, times the C value, 4.1. I'm going to go back and just put my units in here. 0.200 kilograms times 4.18 times 10 to the power of 3 joules per kilogram degree C times my temperature change, which is delta T, T2 minus T1. 15 minus 20, 40 minus 15. Notice that my degrees Celsius, actually I forgot my units here, cancel. I forgot my units at the end here. Degrees C. Notice that my degrees C up here and degrees C down here disappear. My kilograms up here and kilograms in the denominator disappear, and I'm left with units which are in joules. Okay, so now if I go ahead and do my math, I've got 0.2 times 4180 times 25 degrees. I'm getting 2.09 times 10 to the power of 4 joules. Okay, that's the quantity of energy that I would need to add to that 200 milliliters of water. If it's 15 degrees and I want to warm it to 40, that's how much energy I need to add to the water. Okay, so you can see our formula here, our equation for this is going to be a little bit more complicated because we've now got a 4-variable equation where we typically have only had, well, I guess delta D equals V1 delta T plus half A delta T squared. We've had 4 variables in some of our earlier formulas, so maybe this isn't going to be quite as drastic. Okay, if I look back at sample 2, it says an empty copper pot is sitting on a burner. The pot is 1.2 kilograms and is 130 degrees Celsius. The pot is now going to cool to 21 degrees Celsius, and how much energy does it give back to the surroundings? In other words, in order to go from 130 and cool to 21, it's got to lose energy. Where does it go? Probably into the air which is surrounding that copper pot, right? Or maybe if it's sitting on a surface, maybe the surface will absorb some of that thermal energy. Okay, so I'm trying to figure out Q. How much thermal energy is being released. Before, it was how much thermal energy is being absorbed by matter. Now the matter is giving off the energy. Okay, so let's go back to our whiteboard and let's look at sample 2. If I write slower, it seems to work a bit better. So we've got an empty copper pot which has a mass of 1.2 kilograms. 1.2 kilograms. We know that the starting temperature is 130.0 degrees C, and that the final temperature is going to be 21.0 degrees C. Now the other piece that we're told is that it's copper. So if I know that it's copper, I can look up the C value for copper. Oops. C value for copper is right here. It's 3.8 times 10 to the 2 joules per kilogram degree C. So the C for copper is 3.8 times 10 to the 2 joules per kilogram degree C. Now, I'm trying to figure out what is Q. How much energy change is there going to be? Now, it's going to be mc delta T. Notice we're using capital T because it's temperature, not time. Right. I know the mass, 1.2 kilograms, times my C value, which is 3.8 times 10 to the power of 2 joules per kilogram degree C, times my temperature change of T2 minus T1 degrees C. Notice that my kilograms and kilograms disappear, my degrees C and my degrees C disappear. I'm left with units which are in joules, right, which is what I'm looking for when I'm talking Q, because Q is the quantity of heat or thermal energy transfer. Okay, so if I do all the math, I'm getting a value, because it's 21 minus 130, my delta T is negative, right, and my Q will be negative. It's negative 5.0 times 10 to the power of 4 joules. Okay, so that's how much energy is released. Q is negative. It is releasing 50,000 joules to the environment around it. Okay, sample problem number 3. Oy vey. A block of iron starts at 22 degrees C and is dropped into boiling water where the iron will go up to 100 degrees C. Again, if I've got the iron block of metal sitting in water, it's going to be the same temperature as the water. If it's cold water, the iron will get cold. If it's boiling hot water, the iron will go up to 100. It says the quantity of thermal energy required for this temperature change is 4.91 times 10 to the 5 joules. That's how much energy the iron needs to absorb. The question is, how big is the iron block? How much mass does it have? Okay, so back to my whiteboard here. We're going to do sample 3. Okay, for sample 3, we are told that it is iron. The C value for iron, let's just go back to my chart in the notes. Iron is 4.5 times 10 to the 2 joules per kilogram degree C. Joules per kilogram degree C. I am told that the T1 is 22 degrees Celsius. And that T2 is going to be 100 degrees C. So there's T1 and T2. And we are told the amount of energy that's going to be required to do this is 4.91 times 10 to the power of 5 joules. Okay, so there's Q. I'm trying to solve for what mass is the iron block. Now notice here that I've dropped the iron block into water, but I'm not concerned about the water. All I'm talking about in this question is the iron block. So I'm not going to use the C value for water, because even though the water's temperature is going to be maybe affected by the iron, this question specifically is saying what is the mass of the block, what is the C value for the block, what is the temperature change for the block, and this is the Q value for the block. So I can find my mass. If I know that Q is mc delta T, I'm going to take my C delta T from here and I'm going to move it down to the denominator under the Q. So I'll end up with M equals Q over C delta T. Right? And I'm going to put my numbers in now. Mass is equal to Q 4.91 times 10 to the power of 5 divided by C 4.5 times 10 to the power of 2 times delta T, which is T2 100 minus T1 22 degrees C. Notice that all of our temperatures are measured to 1 decimal place. Right? We always use our thermometers accurate to 1 decimal place. Okay, we talked about that earlier in the semester. So the mass is going to be equal to 14 kilograms. Again, because of the C value, which is 4.5 times 10 to the 2 sig digs, I'm going to end up with a mass which has 2 sig digs. Okay, so the C value has to be given. If it's not given in the question, you'll have to look it up. It will be given to you in that table. It's in the textbook, or the one that's in the note that I just gave you. The textbook actually has all of this work in section 8.4. Right, so what I want you to do, cancel, what I want you to do is work on the 3 practice questions that are here in the package. That would be practice questions 1, 2, and 3 here. And then that's for 2.3a. We'll come back to 2.3b tomorrow for Friday. And then I also want you to work on, in our textbook, there are 2 examples that are done for you here on page 261. And then there's another half dozen questions for you to work on here on page 276. And like I said, in our textbook, this is section 8.4. Right, so